Welcome to Ramps and Pulleys. This is my physics end of year lab for Mr. Jockman's class. I'm Isaac Dover. I'll be narrating today. So, the goal of the lab, it was to determine the maximum static coefficient, the mu, of a block on a ramp pulley system that involved two pieces of wood, shown here in the next picture, being brought down by a weight. Here you can see, over here, this is the first piece of wood, and it's going up against this piece of wood. And over here is where the weight would go, and it would come down this pulley, kind of like that. So, when you put the weight here, the goal is to find the most amount of weight the system, the whole thing altogether, can take without this block moving. Alright, so here's kind of an explanation of the forces. Because gravity doesn't behave in an exact way. Over here you've got mg cosine theta because the weight is on an angle. Mg sine theta is always going downhill. Theta over here is the angle, of course, on which the ramp is set, and you can see the system is going this way. So this sets us up to find the mu very well. First, we set up the ramp. We measured the length of the ramp, which was roughly 1 meter. We measured the height of the books that the ramp was leaning against, which was 14.5 centimeters, I believe. And we got the mass of the block, which was already given to us, and we used the length of the ramp and the height of the books to determine, through trigonometric equations, that the value of the angle. So that's step 2. And then we used the mass of the block and the angle measurement, and we set up an equation, which you'll see in a couple slides, and then we solved for the equation, and we tested various masses, and eventually my partner Anna and I determined that the maximum mass at which the block would not move, but it was the most that it would not move at, was 0.044 grams. And we used gravity. We set gravity equal to 10 because that's what Mr. Jockman's taught us to do. It's simpler than 9.8. We found that theta was 8.337 using our trigonometric equations, and we set the m1g cosine theta, which was 1.049 newtons, equal to the normal force, which it always is, of course. And so now all we have to do is solve for friction and the static coefficient. So this was our equation, because as you saw on the free body diagram, the only thing going with the equation that isn't negligible, like tension, of course, is m2g. So we subtracted the force of friction, which is F of F, and m1g sine theta, and which are both going against the equation. And so we all set that equal to the net force, which of course the net force is always mass times acceleration. So we put in m2g, 0.44. We didn't put in anything for a force of friction because that's what we're trying to find. And then we set m1g sine theta equal to 0.154. And of course, since the equation isn't moving, acceleration is 0, and the total mass is negligible, because 0 times anything is of course 0. So we then added f of f to the other side and split it into what it is. So it's really the normal force times the static coefficient. So we're left with 0.44 minus 0.154 equals the normal force times the static coefficient. That leaves us with 0.286 equals 1.049 times the mu. 1.049, of course, is the normal force. So, and then we divide both sides by 1.049, and that leaves us with 0.27 as the mu. And that's about the end of our overall process. So here is the other lab question. So we've got two strings. We've got this over here, that's T2, right? Tension 2, and that's T1. And so we had to find the acceleration in order to find the tensions. And so to find the acceleration, we did the mass, we set up the system here, and then we set the masses equal to, of course, their mg values. So that's 30 and 20, and 30 is going positive, 20 is going negative. So 30 minus 20 is equal to the net force, and net force is m times a, so 10 equals m times a. The total combined mass of all three blocks is 9, so 10n equals 10 newtons of force equals 9 times the acceleration. 10 divided by 9 is roughly 1.11, so that's the acceleration. So now we can plug that into both of our equations, where the net force equals mg of whichever particular block you're solving for the tension, and then you subtract the tension from that. So the net force, of course, is m times a. So over here, it is 2 is the mass times 1.11, and the acceleration equals 20 minus the tension 1. And tension 20 is the mg value. And then if you do a little simple, I guess it's algebra, maybe algebra, you can rearrange it and get T1 equals 20 minus 2.22, which is 17.78. And over here, you do the same thing, different values, 3 and as your m value, and then you get 26.67. And so we find out that T2 has more acceleration, or doesn't have more acceleration, excuse me, has more tension. And that's about the presentation. Thank you for watching.